Okay, so what we want to do is we want to learn some techniques for dealing with integrals that have some trig functions in them. For example, let's suppose, now some of them we already are very familiar with. Like, for example, let's suppose that we've got something like sine x, cosine x. Well, we can handle that, right? Because if I just let u equal sine, then du is cosine x dx, and immediately, we have u du, right? And that's an integral that's easy for us, right? Because it's just the power rule for integration. Okay. So that's one that we've done before that's pretty easy. Now, we've also done those like tangent where we viewed them as sine over cosine, let u be cosine, and solve from there. And those are the types of integrals we're going to look at. But we're going to explore some that are a little more complicated. Now, let's consider this one. Let's suppose that we have sine squared x, cosine x. Now, we use the same technique for this one as we did the previous, right? What we're noticing is that we've got two trig functions here, and they're derivatives of each other, right? So if we let u be sine, then we know that du is cosine. So that tells us right away, well, yeah, it is. Right, 1 minus sine squared is cosine squared. But if we have it set, and in fact, it's a good observation because in a minute we're going to use that to work some more complicated ones. But let's suppose that we have this. So we just let u equal sine x, then du is cosine x, and then immediately we can say, well, then I have 1 minus u squared du. And now we have an easy integral, right? So it's just u minus 1/3 u cubed plus c. Okay, so these are kind of ones that we worked before, just simple substitution ones. Okay. Any questions about that? Yes?
Couldn't 1 minus sine squared x just be rewritten as cos squared x?
Yeah, it could. That's right. But then the problem with that, if we did write that as cosine squared x, we might have a little harder time knowing how to proceed. And that's what we're going to address today. What if we start off having cosine cubed? In other words, think about this. What if we did have cosine cubed? Then we might want to rewrite it this way. So that's exactly where we're going. And two of you have observed that, so that's good. Now, here's what we want to, there's certain trig identities that we're going to need to be familiar with. So let me go ahead and write those down. You're going to need to be familiar with, of course, the Pythagorean identities. Okay? And of course, you can modify that, look at it different forms. Cosine squared x equals 1 minus sine squared x, or sine squared x equals 1 minus cosine squared x. So we'll use the various forms of that. And also, remember, tangent squared x plus 1 equals secant squared x. And cotangent squared x plus 1 equals cosecant squared x. So these are the Pythagorean identities so we need to be familiar with these, right? Because we're going to use these. We're going to refer to these throughout all of these trigonometric integrals. There's a couple more identities that we need to be familiar with. And so we've got sine squared x, and I call this a power reducing identity. Sine squared x can be written as 1/2 times 1 minus cosine 2x. Okay? And cosine squared is like it, except it's 1 plus cosine 2x. So look, what we're going to do, these are the 5 identities that we're going to be working with. And we're going to look at, okay, when do I use each one? Now, I'm going to start off. So I've just shown you some of the trig functions that we can integrate so far, but let's just now go and say, okay, suppose that we have, let's say, cosine squared x. Now notice, this is an integral that involves just cosine raised to an even power. And when we have a situation like that, or it could be sine squared, or sine to the fourth, but the point is, whenever we have sine or cosine raised to an even power, and there's nothing else there with it, what we do is we use this power-reducing identity. And in this case, notice, I just have 1/2, 1 plus cosine 2x. And the reason we do that is because it's easy for us to find the antiderivative of cosine 2x. It's because all we have to do is get the antiderivative of cosine and then divide by 2. Right? So here is how we rewrite it. These are exactly the same. Cosine squared x or cosine, or the integral of 1/2, 1 plus cosine 2x. So here's what we have. We have 1/2. This 1 becomes an x. This cosine 2x becomes a 1/2 sine 2x. And there we have it. There's our antiderivative. So every time you see a sine squared or a cosine squared, you think power reducing. I mean, if it's just by itself in the integral, you think of this power reducing formula. Now that's the only time, right? So if there were a cosine in here with, or if there were a sine in here with this, you wouldn't think of that, right? So what if this had been cosine squared x sine dx? Well, just substitution, right? Yeah, just let u be cosine, and then du, is just going to be negative sine, right? So, but if it's cosine squared by itself, that's where we would use this. Now, they can get more complex. Let's suppose we had sine to the fourth x. Yeah, so if you have sine to the fourth x dx, you view that as sine squared squared, right? So you could say sine squared, or you could write it like this if you wanted. The point is, you have the integral of 1/2, 1 minus cosine 2x times 1/2, 1 minus cosine 2x. And you can see these get kind of intensive. Imagine if you had sine to the 6th power or sine to the 8th. You could work those with this method. They just get a little bit involved. Okay. Now, notice here I have a 1/2 and a 1/2. So that's 1/4, which I'm going to factor out. And now I have these beauties, right? Well, now we need to multiply that out. Okay, so here I go. You're gonna, you got to make sure your algebra boots are on, laced up real tight, and then you just go to work, right? So you distribute, you have 1 minus cosine 2x. And let me make that 2 of them, right? We know how to multiply out a squared. And then plus cosine squared 2x. Does everybody agree with that? I square the first term, 2 times the product of the terms, and then the last term squared. So there we have that. Okay, any questions? Okay, now you may have noticed, I've got a cosine squared over here. Doggone it! We were trying to get rid of that. Well, the bad news is we've got to do this process again. So look, here's what we've got. We've got 1/4, 1 minus 2 cosine 2x. Now I need to rewrite this thing as 1/2, 1 plus cosine. Now watch your bad self here. It's not 2x, it's double what's in there, which is 4x. No, because there's a 2x in there. Remember, the formula calls for you to double what's in there. And if there's a 2x in there, it's going to be 4x. See? Harken back to the formula, see the formula up here. See, if it's x, this is going to be double it. Okay. Yeah, okay. Okay, now we've got finally something that we can work. So here's what we've got. We've got 1/4. Now, okay, that 1 just becomes x minus just a sine 2x, right? Okay. And then here we go, plus 1/2 x, right? If I distribute this 1/2 through. And then over here, plus 1/8 sine 4x plus c. And there you have it, right? Does everybody see? So this right here was 1/2 cosine 4x. But when I got the antiderivative, it's 1/2 sine 4x divided by 4, right? Because I have to, divide by whatever's inside the cosine. Okay, does everybody see that? Okay.
Where does the x come from for 1/2 x?
Right here. This is where we get the 1/2 x, right? Because we just have 1/2 and that antiderivative would be 1/2 x. Okay, any questions about that? Okay, now this is if you have sine raised to an even power and nothing else, or cosine raised to an even power and nothing else. Now, let's suppose that you don't have sine or cosine raised to an even power. You have something like this, cosine cubed. Well, yeah, when you have this, notice this is just an odd power of cosine. The easiest thing for us to do is remember these Pythagorean identities. Because if I peel off a cosine, and I got cosine squared x cosine x, let me see here, cosine x, okay. Now, this brings us back to what we observed earlier, that I can rewrite cosine squared x as 1 minus sine squared x. So I can write this as 1 minus sine squared x cosine x, and then I let u equal sine x, and it's over, right? I mean, we just worked that problem a minute ago. So, does everybody see that? Now, that's true if we had cosine to any odd power. We can always peel off a cosine, right? And then use this Pythagorean identity. So, for example, let's suppose that we have sine to the 6th power. To the 5th power. Sorry about that. This one right here? Well, let's go ahead and finish it off. So what we have then is we have 1 minus u squared du, right? Which would be u minus 1/3 u cubed plus c. Like that. Now, so let's suppose we have sine to the 5th power. Well, still, just peel off a sine. Whenever you see these, you think automatically, if I can just write sine as an even power, now I can put sine to the 4th in terms of cosine, right? Because if you have an even power of sine, you can put it in terms of cosine. So here's what we've got. Well, think of it as this way. Sine squared x squared, right? I'm putting in that part. You don't have to put in every step. But you see now that when I put it in that form, I have 1 minus cosine squared x squared sine x. Well, if you use the power reducing, you still have this problem is that you still have the sign up here, right? So even if you tried to use power reducing for sine to the 4th x, you could do that. You could reduce it to just first powers, but it wouldn't help you with the integral at the end because you have that sign. Okay, now once we do that, we just go back to our substitution. I'll let u equal cosine x. Then du is, of course, negative sine x. Right? Not exactly what we want. We got sine x, not negative sine x. So I'll just do negative du. Okay? And then, huh?
Why do you pick u as cosine?
Well, I picked u to be cosine x because I noticed that if I've got this right here, and this is just, that's just the derivative. That's almost the derivative of cosine. So I figured, okay, I'll let u be cosine, then du will take care of the rest of it. So this is what I have now. I've got a lovely integral. You know, we got a nice smile on our face when we get to this part. Ah, that's nice, because we know how to deal with these, right? I just multiply that out and then use the power rule for integration, right? So dig this. Now I've got negative in front, 1 minus 2u squared plus u to the fourth, right? I just, you know, kind of multiply that out. Yeah, du. Thank you. Thank you. Boy, I appreciate that. Y'all catch stuff. Okay? Any questions about that? Okay. Now it's easy for us, right? Okay, so I mean, I almost feel sorry for this integral at this point because it has nothing left. No fight left whatsoever. U minus 2/3 u to the third plus 1/5 u to the fifth plus c. Whoops, plus c. Come on now. Ah! There we go. Okay, does everybody see that? Any questions about that? Okay, now notice what we had here. This is when we started off with just sine to the fifth power. And that's how we dealt with it. So we've had even powers of sine and cosine by themselves. We've had odd powers of sine and cosine by themselves. Now let's mix and match here. Let's suppose that I have something like this. Let's suppose I have sine to the third power, cosine to the fourth power, let's say. Okay. Now I've kind of matched, mixed things up. I've combined them. Well, you don't want to use power reducing. Definitely not. Because, yeah, you could use the power reducing formula for that, but all you would do is generate a mess. It wouldn't help you get to where you're wanting to go. What you want to do is you want to be able to let u be either sine or cosine and du be the other part. So if I look at this and I think, hey, if I peel off a sine, I'm going to have sine to the second power, which I can write in terms of cosine. And then I'll just have everything in terms of cosine except the sine dx, sine x dx on the end. So look, here's what I'll do. I'm going to just... Now, what I don't want you to do is really try to memorize steps. I want you to just get the idea of what we're trying to do. Just, utilize your Pythagorean identities to get these things in a place where you can solve them. So now we have cosine to the fourth x sine x. This is nice. Because I can rewrite sine squared in terms of cosine. Okay? And then, of course, I have cosine over here. Now's when the smile comes, right? You just start grinning, right? Because you say, I got this integral. Because now you let u be cosine, and du, of course, negative sine. Same old stuff we've done so many times. Negative du. And look, that's that right there. Right? So look, I've got this now. I've got negative 1 minus u squared, u to the fourth, du. Yeah. So it's now easy. So one of the main reasons we learned trig identities was to tackle things like this, right? So we don't like, we don't like this problem. We don't like the way this looks. Whoops. We don't like the way, maybe I can, I can't do it. Okay, my board doesn't, okay, let's just leave it. Okay, maybe I can, there. Okay. You don't want that. Now, so here's what I have. Now here's what I'm going to do. I'm going to, I guess now I'll just say u to the fourth minus u to the sixth and du. Super easy now. My goodness. So now we have negative 1/5 u to the fifth minus 1/7 u to the seventh plus c. And you can distribute the negative through if you feel like it. Okay? How's that? And of course you can all, now look, a lot of times, well, no, let me not say that. You can substitute, of course you can substitute back in, whatever you let u be, you can substitute back in. Sometimes, depending on what you let u equal, your answer is going to look a little bit different. Okay? So sometimes there's an option, let u be sine or let u be cosine. So you might get a little slightly different answer than someone else that worked the same problem. But it's just because if that happens, check back and see what did we let u equal, right? Okay, now, there's where we have sine and cosine together, and that's the general idea. Now, there's another type of problem that you'll see, and that's when we have tangent and secant together. Okay. So, let's look at this. Let's suppose we have tangent cubed x, and let's say secant to the fourth x, something like that. Okay? Okay. Now, it's just like when we see sine and cosine together, we're thinking, I'd like to let u be one thing because du is going to be the other. But the problem is they're raised to these powers, so I need to get it to where I can just let u be either tangent or let u be secant, and then du will be the rest of it. Now, remember that the derivative of tangent is secant squared, and the derivative of secant is secant tangent. Okay? So if I look at this, I'm thinking, man, if that were tangent squared, I could write it totally in terms of secant. And I would like that very much. See, so let's do this. Let's say tangent squared x, okay? And then, I got secant to the fourth over here. I don't know. I forgot. I forgot to put I can't just get rid of tangent. Okay, now, so there's what I have so far. But that's not exactly, because that's not the derivative of secant or anything, right? It's just tangent out here by itself. So what else? What else could I do? I can rewrite tangent, right, as a secant squared x minus 1. And then, well, what about this? Yeah, that's right. Just take out a secant. Yeah, see? That's brilliant of us, isn't it? See? Look how brilliant this move is, right? Because now, dig this. We can let u be secant. Then du is secant tangent. There it is. Because now we have a nice integral that anybody could solve, right? We have u squared minus 1, u to the third, du. There. See? And so these trig identities, this is where they really, you can start to see, yeah, I can see why those are important. And we're going to see other ways too, in the next section, but this is one of the ways where you really start to see, man, I'm glad I took trig. We've got u to the fifth minus u cubed du. Okay? And now, of course, it's the easy part. Okay? Does everybody see that? Any questions? Okay, now you can let's suppose let me. Okay, so let's look at this. Let's suppose that we've got let's say let me see. Let me think of one. Well, I tell you what. Let's do this. Let's do this one. Let's do tan cubed x secant. This is one we just did, right? I was thinking, okay, so we can do. Yeah, let's do this one again. Okay, so look. Did we just do? Yeah, this is the one we did, isn't it? Okay, so what's a different approach we might be able to take on this one?
Instead, put secant in terms of tangent.
Yeah, what if we do this? What if I do this? What if I say, okay, I'm going to take, let's see here. If I, well, let's see here. If we take out, okay, so if I peel off a secant, right? Okay, so look, so I've got tangent cubed x, and I've got secant, what do I have? I have secant squared x, secant squared x. Okay, is this going to work out for us? What do you think? Is that going to work out? Well, tell me what I should do next. Now, what is the derivative of tangent? Man, this is tantalizingly close, right? Tangent squared minus plus 1. I can do this, right? Now, if I do this, and I let u be tangent, ooh, we're there, right? Mercy. This does it, right? Okay, is it that simple? We've got u cubed, u squared plus 1 du. Really? Now notice, it's the same integral, but we just took a different approach, right? Okay, just a slightly different approach. But we've got u to the 5th plus u cubed, and that's an integral, right? And then du. So what do we get? We get 1/6 u to the 6th plus 1/4 u to the 4th plus c. Now, does that look like our previous answer? Yeah. But you realize u is equal to something else, right? What was our previous answer? It's the same. It's a minus?
It's a minus and the other.
Okay. So you see, we addressed the same integral, but we got something that looks a little different. So that's why I say earlier, you want to look back and make sure, if you're comparing your work with someone else or in the back of the book, you want to make sure that you let u be the same, because your answers will look a little different. But if you plug back in, if you plug in tangent for u here and secant for u in the previous, and you work, it will work out using some identities to the same. Yeah, I mean, the difference in those would be by a constant, right? Okay, any questions? Okay.